Hello. Over the next few minutes, I will attempt to explain the basics of a useful tool in both statistics and engineering called linear probabilistic modeling. So this is a typical example of what a linear model would look like. When the expected value of y can be approximated as a linear function of x, we can use a linear regression model. This line, called the linear regression line, follows the form y equals b naught plus b1x plus epsilon, which is very similar to the linear function y equals mx plus b. The epsilon of a data point would be its error, which is negative when below the regression line and positive when above the line. So if we were to fix that value of x, the only variable that would determine the y-coordinate of the linear model would be the value of epsilon. If each point were to have a normal distribution of possible values, then the equation y equals b naught plus b1x would give a linear regression model of the mean values of each point's distribution. So here we have the data set for my chosen example, which is showing the relationship between the barrel length of a rifle and then its resulting muzzle velocity. So we can see here that as the barrel length increases, the resulting muzzle velocity also increases. Here we have the distribution of the muzzle velocity given a 24-inch barrel. We can see here that the expected value of the muzzle velocity is around 2,950 feet per second, but that muzzle velocity can stray above or below that expected value given a number of factors. So here we have our expected values plotted against our actual values, and that's shown here by the orange line, our linear regression line, shown against the blue dots. The blue dots are our actual values. And then you can see the difference here between the orange line and the blue dots. That's going to be the error. There's a clear linear relationship between these two statistics, that is the muzzle velocity and the barrel length. And we can see that there's roughly a 30 to 35 feet per second increase per inch of barrel that you're going up. The error can be accounted for by flaws in the rifling of a barrel or slight differences in the temperature of the barrel or the surroundings, elevation above or below sea level, and extremely small differences in the amount of powder in each cartridge casing. It's up to engineers to determine which factors cause each kind of error and whether or not they are acceptable. For example, as the barrel heats up, the barrel expands, and some of that pressure that's pushing the bullet can escape and cause the bullet to actually slow down or not reach its full projected velocity. So a lot of these slight negative errors here are probably okay if we were doing actual testing or actual engineering. Thank you.